Thank you for joining us for the Consulting Specifying Engineer webcast, HVAC Systems that Achieve Indoor Air Quality, sponsored by Aegis. I'm your moderator, Amara Razgis, with Consulting Specifying Engineer and CFE Media and Technology, and I'll be with you for this hour-long education session. Let's learn about this platform first. If you're having trouble with the slides or with the audio, please refresh your internet browser or click on the Refresh Media button. It's directly under the presenter's photo. You can control the volume settings by adjusting the volume on your own device. If you're having technical problems, please click on the question mark at the top right corner of your screen to do some system checks before contacting a technician. If you do need a technician, please type a message into the Ask a Question box and we'll respond in the Answered Questions box. To download the presentation, use the Event Resources tab on the left side of your screen. Type questions for the presenters in the Ask a Question box on the left side of your screen. You may ask questions at any time during this presentation. The interactive Q&A portion will start in about 45 minutes. If you're interested in earning one AIA learning unit, for this event, you must pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab at the top of your screen. The quiz will open in a new browser window, so I recommend you open that tab right now so that you can take it when the webcast signs off. In keeping with the American Institute of Architects Quality Assurance, please take a moment to read the quality assurance slide. All right, well, here are the learning objectives for today's event, and we'll talk about these during the presentation. Please note that any red underlined text that you see is a hyperlink in the PDF where you can get more information. Now, let's hear from this session's sponsor. At the conclusion of the commercial, you may experience a few seconds of silence to make up for different internet speeds. Please stay tuned for today's presentation after the commercial.
VFDs can save 30% or more in energy costs, but VFDs can damage motor bearings. Without shaft grounding, VFD-induced voltages can discharge through motor bearings, causing damage such as pitting, frosting, and fluting, and unplanned motor failure in as little as 3 months. Aegis shaft grounding rings provide proven long-term protection against VFD-induced bearing damage. By channeling harmful shaft currents away from bearings and safely to ground, Aegis rings ensure that motors last for the full L10 life of their bearings. And while you can install Aegis rings yourself or have a motor repair shop install them, the easiest way to protect your motors is to purchase them with Aegis rings factory installed from any of a growing number of motor manufacturers. To protect VFD motors, always specify Aegis rings. To learn more, visit the Aegis website and schedule a lunch and learn worth 1 hour of professional development.
All right, well, we've lined up two fantastic presenters for today. Benjamin Skelton is the founder and president of Cyclone Energy Group, a Chicago-based energy services company. He focuses on executive account management, strategic growth, technical direction, and a variety of other things. As a consulting engineer, Benny specializes in energy efficient and sustainable buildings and is recognized as an expert in building energy simulation and building commissioning. He's a frequent presenter on HVAC, energy efficiency, and similar topics. He was a 2015 Consulting Specifying Engineer 40 Under 40 Award winner. Matt Short is a project manager and mechanical engineer with Smith Seckman Reed in Houston. He has spent his career in the MEP consulting industry designing mechanical and plumbing systems for a variety of facilities, including municipal, aviation, and healthcare. His current focus is managing and designing projects for healthcare facilities over Texas and Louisiana. Matt is a member of the Consulting Specifying Engineer Editorial Advisory. All right, Benny, you are up first. Go ahead.
Great. Thank you, Amara. Really appreciate the opportunity to speak here today. The presentation, we're going to start with a bit of a journey of the indoor air quality within buildings. So excited to present with Matt and go through a lot of different HVAC systems in buildings, but I thought we'd start with a little history of where ventilation started, at least here in the United States. The buildings used to be, the older buildings used to breathe on their own. They had operable windows. We didn't have mechanical ventilation for them. The facades would allow for infiltration. And that's how buildings existed, because we didn't have means for cooling or treating the air. We could heat air typically, but we couldn't necessarily to cool it to create a good environment. So people controlled the quality of the air. Just taking a look at Chicago's Central Business District. This is kind of an interesting example of, you can see older buildings and newer buildings together, but I've highlighted some of the older buildings in red here that have area wells. The area wells were these giant buildings that can take up an entire city block, but they needed to get air in the interiors. And when you didn't have means of mechanical ventilation, the buildings had this hollow core where they could have video, and they could get they could have the lights, and they could have the air quality coming in and be controlled. The newer buildings you see are all enclosed and don't have that same need for natural ventilation. When things started to change in the 20th century, there were two characters in history, one of them being Willis Carrier, the father of air conditioning, invented the mechanical centrifugal refrigeration machine and introduced that into the marketplace in the 1920s. And there was an architect named Ludwig Wies Manderow. He was a modernist architect and one of the first of his era to really come up with a building that really changed the way things looked. The modern architecture has shifted into this all glass kind of building structure that you see here on the right. Now, I bring this up because it changed the way that buildings were ventilated. Mies and Willis had a good relationship with each other, to where Willis would build whatever machine he needed for Mies's buildings to be cooled, and mechanical refrigeration helped with ventilation in these buildings at the time. So this really changed the era of architecture. This style of architecture was introduced in the 20s, but then really became popular in the 1950s. And so what we found with buildings of this era was they got tighter. They didn't breathe on their own anymore. And now we started bringing air into the buildings. So moving forward into the 1970s, 20 years or so after these buildings had been started to being built, they were bringing in ventilation, and some things started to happen. We found that there was an energy crisis in the early 1970s, and to save energy, a lot of buildings cut back on the expense of mechanically ventilating their buildings and reduced the outside air. In 1984, the World Health Organization introduced a syndrome called sick building syndrome. And this was a result of contaminants in buildings not being properly ventilated. ASHRAE created a couple of standards in parallel in the early 70s to start to address these conflicting interests, I guess. The ASHRAE 62 1973 standard looked at indoor air quality, and that standard has continued to evolve. We're going to talk a lot about that in some application here later in the slides. And at the same time, ASHRAE also introduced the first energy conservation standards. So the idea here is these two standards, while one promotes minimum ventilation, the other promotes minimum energy consumption. But I think, in my opinion, largely over the last 20 to 30 years, we found that indoor air quality has kind of remained stagnant at this minimum acceptable ventilation level at the cost of looking for more energy efficient, more sustainable buildings. So that's where we really are coming into the current day. We saw a lot of focus on programs that looked at purely at energy efficiency, or maybe had a portion of the air quality highlighted, but it definitely wasn't a focus. And we're starting to see now, especially after pandemic year, that air quality has shifted into the focus. We're going to talk a lot about mechanical systems and HVAC, but the concept of what is indoor air quality, is there good air quality? That definition doesn't really exist. What we have are things like the ASHRAE Standard 62, some other standards Matt will talk about, that identify what is acceptable air quality or help you identify what meets the standard, but it doesn't necessarily define what is good. And there are a lot of different things in the air. Every building has different things that could be monitored. So as we have this conversation, you have to have an open mind that there's different definitions depending on the type of building that you have, where it's located, and the type of equipment that you're going to put in it. So Mara, I think this introduces our first poll.
Yeah, exactly. So to understand better what type of building this audience is working in, we've got a quick poll for you. For which of the following types of building structures do you specify, design, or make product selections? And that will allow Matt and Benny to better provide information during this presentation on those building structures. So if you could take a few seconds to answer it, we would appreciate it. And moving on, Matt, you're up next.
Great, thank you, Amara. So now that we've established the history of indoor air quality, I'd like to spend a little time further defining exactly what is indoor air quality. And as Benny previously mentioned, indoor air quality is as simple as it sounds. It's providing quality air for the occupants within a certain building that we're designing. To be able to do this, there are really two elements that we primarily focus on. First is controlling pollutants. These are pollutants that can exist both in the outside air being brought into the building for ventilation purposes, or pollutants that may be created inside of the building by occupants or processes. Some examples of pollutants that are often present are fumes from cleaning products, tobacco smoke, combustion air, and outdoor air pollution that may be brought in with ventilation air. Indoor air quality also includes conditioning the air so that spaces are comfortable for the occupants. Proper conditioning of air includes adequate filtration, reduction and control of space humidity, and then obviously temperature control. The chart below is actually from the Texas Commission on Environmental Quality, which uses the EPA's Air Quality Index to describe outside air cleanliness for various locations and dates. On that chart, you'll see both green and yellow. Green indicates a good or clean outside air environment. Yellow is sort of moderate. And then what's not shown there, which is a good thing, is orange to red is unhealthy outside air conditions. You'll see for the city of Austin on Sunday, July 7th, that the AQI references what's called PM 2.5. PM 2.5 stands for particulate matter that exists in the outside air, which is 2.5 micrometers and smaller. So this is a tool that's helpful to sort of gain an understanding of the outdoor air pollution that might be considered when you're designing a building. A special type of occupancy for consideration is a hospital or healthcare facility. In addition to what we mentioned on the previous slide, providing quality air in these types of buildings will also include protecting patients who may be immunocompromised and the staff that cares for these patients. Additional considerations for designers of these types of projects will include some of the following items, such as protecting against infections, protecting against viral diseases, which has obviously been a major concern over the past year and a half, removing potential building contaminants, controlling harsh odors which may exist in a healthcare environment, and then providing proper waste removal procedures, which may include biohazardous waste. So now that we understand exactly what indoor air quality is, I'd like to discuss in greater detail the codes and standards that apply to these design considerations that Benny introduced earlier. Starting out with ASHRAE Standard 62.1, this is a standard that's recognized almost universally as the industry standard for indoor air quality. Within this standard, designers will have access to guidelines for temperature, humidity control, building pressurization, and many other design criteria that's impactful for indoor air quality. One of the most commonly applied and useful tools within this standard is the minimum exhaust rate and ventilation table, which is table 6.2.2.1. This is a table that provides guidelines for various spaces that'll help the designer determine a minimum amount of fresh air to provide to a space and the required exhaust air to remove from a space. Moving on, for healthcare facilities, ASHRAE Standard 170 provides design ventilation standards for specific healthcare spaces. This standard will include filtration requirements, air change rates, pressure relationships very similar to 62.1, but it'll focus primarily on healthcare. In regards to the filtration requirements, Table 6.4 provides a standard for filter MERV ratings for equipment serving various healthcare spaces. And it's important to mention that ASHRAE Standard 170 is referenced by the Facility Guideline Institute, or FGI, which we'll discuss further on the next slide. Continuing on guidelines that are specific for healthcare facilities, this document is called Guidelines for the Design and Construction of Healthcare Facilities. It's a very important document to be familiar with if you're designing HVAC systems that serve a hospital or healthcare facility. As I mentioned on the previous slide, this document is published by FGI, or the Facility Design Institute. The document not only covers HVAC, but it also has design and construction criteria for architectural, medical gases, and electrical systems. This is a document that is widely used across the country to verify construction and operation of licensed medical facilities. And once again, just wanted to point out that this document does reference ASHRAE Standard 170 as the ventilation standard for healthcare facilities. It's also important to note that in many states, the governing body may adopt and amend a set of guidelines that are used to design and construct a healthcare facility. For example, in my home state of Texas, THHS, or Texas Health and Human Services, utilizes Title 25 of the Texas Administrative Code and Chapter 133, which covers hospital licensing, to review plans, inspect newly constructed or renovated facilities, and ultimately provide a license to practice in the facility. Facilities must obtain a license before admitting patients. Therefore, adhering to these local codes is incredibly important. In addition to this, a facility must maintain the operational requirements to maintain the hospital's license. In subsection 1 of this chapter, the construction requirements are included. This chapter references similar guidelines that were discussed in the previous standards. However, amendments may have been made based on local facility needs. An example of these amendments can be found in the ventilation tables, which in the Texas code, which I mentioned earlier, is Table 3, where some spaces may have different required air change rates than what's described by ASHRAE Standard 170. And so now, Benny, I think you'll discuss further requirements on indoor air quality.
Yeah, thank you. Looking outside of healthcare, as we mentioned earlier, every building has different requirements. Commercial office building, for example, I saw in the poll, it seemed that most people work with office buildings. There are a lot of different types of systems that you can install or design in these buildings that have good air quality effectiveness to them. And it doesn't have to be just new buildings. It could be existing buildings and retrofit environments. One example of that, and probably one of the more typical examples we see in an office building, is the overhead variable air volume distribution system. This type of system, generally speaking, fully mixes the space, meaning all of the air is changed over consistently within the space. It has a less of a ventilation of effectiveness, though. You can see as far as getting ventilation to the occupant, we need to factor that in. So when you look into the calculations within ASHRAE 62.1, we have to increase the amount of ventilation to distribute to spaces to try to, from a calculated procedure, estimate how much ventilation is actually getting to the occupant zone. When we look at another type of system, displacement ventilation, often referred to in offices as underfloor air distribution. This tends to create a stratified zone. So the air is introduced at the occupant level, typically at the floor or at the desk level, and comes directly into the occupant space. So they're getting fresh air. They're getting 100% of the effectiveness of that. And the air above the occupied zone, maybe 6 foot or so, is stratifying. It's not being mixed or it's being extracted. But there are other systems out there, but those are 2 examples of that. You can also look at dedicated outdoor air systems that directly bring ventilation into spaces if you have concerns. That in a lot of new office buildings, we might look at zone level equipment, a heat pump, a fan coil, or even a VAV system still, but we'll have dedicated ventilation brought to the space. There are several control strategies that can also impact indoor air quality. When we look at commercial office buildings, demand control ventilation is one of those. Demand control ventilation controls the ventilation based on occupant demand. And the way that we see occupant demand is through CO2 or carbon dioxide. There aren't really any other sources in buildings that introduce carbon dioxide levels. So it's a very good indicator of how many people you have in a space or within the building. This is best and most effective on the zone level. For instance, if you have a conference room and the CO2 levels get very high very quickly, you're going to want to bring more ventilation into that through your automation system. In some climates, we can optimize and use economizer operation. I'm in Chicago, and we're able to use economizer all winter. So we control the mixed air temperature of air handling systems using fresh air. And so we're actually bringing in more than the minimum ventilation rates. But when it's a day like today and it's 95 degrees Fahrenheit and very humid, we don't want to run that economizer. So we go back to the minimum ventilation strategy. But there are ways to kind of stretch the zones of that to bring more fresh air in and not penalize your building with energy costs. And we'll talk about this more later on when we get into some of the a little bit of the COVID response things, but purge ventilation is also another strategy you can do for buildings. Often at night, buildings are cleaned, and you want to get rid of that cleaning chemical before people come back into the space. So purge ventilation can be very effective. When you look at multifamily high-rise buildings, these buildings have more challenges than just air quality when it comes to ventilation. Building pressurization is typically one of the biggest challenges when you come into high-rise and tall building design. Not just office buildings, but multifamily high-rise buildings have more challenges because they generally have operable windows. And now, instead of an automation system that's controlling the dampers and bringing the ventilation in automatically based on sensor data, you have a person that has the ability to change the whole dynamics of the building just by opening a window. And so when we look at these buildings, it's trying to balance makeup air, it's trying to balance exhaust, but it's also trying to manage the natural stack effect of the building. Stack effect occurs in a building due to its height, based on temperatures, indoor to outdoor, wind speeds, and of course, people. And poor design is one thing I put on here. If you have things that directly expose lobbies to stairwells, elevators, things where there aren't pressure breaks or things to help manage the stack effect, that's going to impact your air quality. One of the things we deal with a lot in multifamily buildings is odor control, odor from other units infiltrating into other people's units because of things related to stack effect, building ventilation, and such. So generally, these buildings have a makeup air unit and exhaust systems, all with variable speed drives, and those modulate to try to control pressure at different areas and levels and manage this stack effect. You can't control stack effect. You can't tell it what it's going to do, but you can try to manage your building as best you can. And just a very brief overview of a stack effect case. You know, the neutral plane of your building. This is where you switch from the part of the building being negative to the top part of the building being positive, or vice versa, depending on temperature differences. That neutral plane changes constantly depending on temperatures outdoors and the wind speeds. And so you need to have your building set up in a way to monitor certain metrics at certain levels of the building to understand what is happening and to be able to adjust to that. And then another example is retail and light commercial sector. Often these buildings are somewhat neglected when it comes to quality HVAC systems. Generally speaking, a lot of them get packaged rooftop units, which have limited functionality when it comes to being able to do other things like demand control ventilation, for example. They tend to be constant volume distribution systems. So, and what we see in a lot of retail applications, restaurants, things of that nature, is they'll be on thermostatic controls that cycle. So the fan and the ventilation will only operate when there's a demand for cooling or heating. And obviously in a populated area, that's not the proper way to manage that. And then Amara, I think we'll go to our second poll question.
Exactly. Yeah. And you alluded to this, Benny. The first poll question asking what kind of building types this audience is working in. The number one building type was office buildings. Close second was hospitals and healthcare facilities. And then third was government buildings. So before we get to our next question, now we want to talk about systems. So this next question is, what is the number one type of HVAC product or system that you currently specify? So if you'll take this poll now and let us know what you're working in that would be fantastic. That'll also help us as we move on to the next part. And moving on, that's you, Matt.
Thanks, Amara. So before we dive into the systems, I think it's important that when you're beginning a new project, it's important for a designer to reflect on what is the ultimate goal of the facility as it pertains to providing quality air. So in new buildings, one of the obvious goals that Benny touched on earlier is preventing sick building syndrome. Sick building syndrome occurs in a building in which indoor air quality was not properly considered or maintained, and it can lead to unsafe and unhealthy conditions for a building's occupants. As you can see in the chart to the right, some of the primary causes of sick building syndrome are inadequate ventilation and contamination from both inside and outside sources. These three items alone make up approximately 80% of the most common causes of sick building syndrome. To prevent this, designers should consider some of the following steps when beginning the design of any new facility. First, determine the required codes and establish the minimum criteria from the most stringent code that applies. This will help create a ventilation baseline for the facility. Next, work to establish equipment level zones, determine how the building should be conditioned. From there, determine the code required level of filtration for each of these zones. Taking the facility baseline, we can then understand the minimum ventilation rates for each zone based on the space requirements within each zone. Next, it's important to determine which spaces require air to be exhausted from the building and how they interact with any adjacent spaces. And then finally, perform an air balance study at a local and total building level to ensure the building is properly balanced and positively pressurized to combat infiltration. For a renovation project, indoor air quality is equally as crucial. In fact, it is common practice to start with a review of existing conditions so that you can fully understand and rectify any current deficiencies. Designers should consider some of the following tasks when beginning the design of any renovation project. Ensure any renovation project is designed in considering the most current codes that apply to the renovation. Try to determine if there are any problem areas in the building that the owner may have had issues with in the past. Common issues that we see often are hot spots within the building or areas of the facility where relative humidity might be difficult to control. These are often identified with excessive amounts of condensation, things like that. Take a tour of the current facility and familiarize yourself with the space, how it's being served, and from what equipment or systems. Even if you're intending to remove the equipment or systems, it's important to assess these areas so that the newly specified and constructed systems don't experience the same issues. If it's available, it's helpful to troubleshoot trend logs from the building automation system, especially for some of the areas the owner might identify as a problem area of the building. And finally, when designing a renovation project, adequate space, access, and location for new equipment is not always ideal. Pay close attention to these details, as often some of the most critical processes to maintaining a healthy indoor air quality is simple and routine maintenance, such as filter replacement. After establishing goals for our projects, we can discuss design criteria to consider for some of the topics we discussed previously. In regards to ventilation, often the pathway of fresh air from intake to equipment can create challenges after installation. Consider nearby contaminants and observe code-required distances from these contaminants. Common examples of these types of contaminants are plumbing vents, generator exhaust, and other exhaust sources. It's also important to consider the path of fresh air from the exterior of the building to the location of your outside air intake. What I mean by this is consider how neighboring facilities, obstructions, and prevailing winds might have an impact on the quality of fresh air that we provide to the building. The image below indicates a prevailing wind study, which shows potential pathway obstruction for a building's outside air intake. A wind study like this is more effective and recommended for outside air intakes on a facility that's being constructed in a congested urban environment. Additionally, we should consider the outside air path to the air handling equipment to ensure that airflow is not restricted and fresh air can be properly supplied to the space. Once the path of travel for fresh air is established, we can calculate the required amount of ventilation air for the building and for each individual piece of air handling equipment. Start by reviewing the applicable codes. Establish which codes or standards are the most stringent for each space to ensure the space is effectively ventilated. These ventilation rates can be described in CFM per square foot, CFM per occupant, or air changes per hour, depending on which code you're referencing. Once the required ventilation is determined, perform an air balance analysis with outside air versus exhaust air to ensure that the space, level, and total building are properly pressurized. Ensure a positively pressurized building to protect against infiltration. It should be noted that you should be cautious not to overpressurize the space, which can cause side effects such as door closers not operating properly. So Benny, can you discuss some of the design considerations required for natural ventilation?
Absolutely. Natural ventilation is one of those things that, we talked about at the very beginning in the old history of buildings. We open the windows and we bring in fresh air from outside. So in more modern buildings, now that we're doing more mixed mode kind of ventilation strategies where you'll be bringing in mechanical ventilation at some times or natural ventilation at some times or both at the same time, there are a lot of considerations you want to take into account. So for example, we want to maintain the comfort levels in the space. ASHRAE has a standard for what defines comfort levels as well. The considerations we will look at are very application specific. An office is going to be different than a residence, different functionalities, different uses, different temperatures. So when we look at it in a commercial grade application where we're going to have an automation system control this, we want to make sure that the weather outside isn't going to make weather inside. And that can happen very quickly. Weather can change when a storm passes over, things of that nature. So generally, we will have a nice weather station on site that looks at things beyond what we normally look at in a lot of buildings. Temperature and the humidity, we either measure the dew point or calculate it. And then we look at wind speed and, of course, precipitation. A lot of people don't like having automated natural ventilation systems on their building because if something doesn't happen right and it introduces the wrong conditions of the air, you might get condensation on flooring surfaces and create a dangerous environment. But it can be done effectively. But you just want to make sure that you look at these parts in the application and make sure that it's tested and it works well. Some people only want to see this when occupied, and there's some climate zones where you can't really effectively design natural ventilation because of the outdoor temperatures. It'll never provide that conditioning that you want to have inside your building. Matt, I'll let you take filtration.
Thank you. So for a healthy indoor air quality, filtration is one of the most important items we can consider in our designs. HVAC filters are rated by MERV ratings, which stands for Minimum Efficiency Reporting Values. The chart that you see on the right indicates a filter MERV rating and its associated average particle size efficiency in microns. These are some of the items that are in the codes that we discussed earlier, and it's important to refer to them as they're specific to a different facility, whatever you may be designing, as some of them have specific requirements for filter MERV ratings that serve a particular space. In air handling equipment, the following filter types are most common. Starting out with pleated panel filters, these are typically used as a pre-filter to capture some of the larger particles that we see in the outside airstream. We most often see these specified as a MERV 7 or MERV 8 filter rating, although we have seen that increasing lately. These filters do load quickly as they're capturing the larger particles in the untreated airstream and will need to be replaced more often by the facility owner. Moving on to cartridge type filters. These are often used as a final filter to capture smaller particles. We most often see these specified with a MERV 13 or 14 filter rating. These filters do load at a slower rate than the pre-filters, but they do have a greater resistance to airflow. And because of this, it's very important that we consider a loaded or dirty filter when doing your static pressure calculations. And finally, to touch on cartridge type HEPA filters, HEPA stands for High Efficiency Particulate Air Filter. These are also commonly used as a final filter, most often in units that serve critical spaces such as operating rooms. These filters are capable of removing 99.97% of particulate matter, and they are technically considered a MERV 17 or higher filter rating. So Benny will now kind of walk through some of those images of the filters we just discussed.
Yeah, Matt, they can take lots of different shapes and sizes depending on the type of HVAC system that you're going to be putting them in. The different filtration efficiencies that Matt just went through can apply to pretty much any type of HVAC system as long as you've looked at the design pressure drop. You can have these on your home furnace. You could have them in an rooftop unit. Can have a MERV 13 filter. In big office buildings, we have been recommending MERV 13 filters for a long time, especially buildings that are seeking a LEED certification or something along those lines, where that's one of the credit requirements. But in the recent past, we've been asked, can we get even higher filtration in our building? We have to look at each application to see if the cartridge filter is, or the bag filter or the pleated filter is going to be applicable. From an energy standpoint, we want to try to maximize the efficiency of the filtration for the building, but we also want to try to minimize the energy consumption. These filters stay in place; they're a constant draw on energy. In a lot of bigger applications, we found that there are a V-bank or a V-shaped type filter that can replace some of the bag and cartridge style filters and provide up to a MERV 15 quality, and that can actually reduce some of the energy costs of that application.
Thanks, Benny. So when designing a system with virus control measures in mind, such as COVID-19, the typical filter requirements still apply, although we are seeing advanced measures taken for these spaces, as Benny just mentioned. Again, what we're often seeing for these types of systems is still a pre-filter to filter your outside airstream. This can be a MERV 7 or 8 filter, all the way up to 11 is typical. It's also common to consider, like I mentioned, a MERV 11 to 13 pleated filter for this application. Consider providing a HEPA filter and air handling equipment to use as a final filter for air before being supplied to the space. And then depending on the location of the exhaust fans and the exhaust air discharge, consider filtering your exhaust air as well. This is actually code required for exhaust fans that are located within maybe a mechanical penthouse or within an enclosed space that discharge to a louver. If the fan is inside the building, it is required to provide a filter on the exhaust airstream. For equipment disinfection needs, ultraviolet light is commonly used in HVAC equipment. The most common application of UV is to install the UV lamps in conjunction with the cooling coils and air handling equipment to prevent fungal growth. An example of this type of installation is in the image to the right, where the lamps are shown installed downstream of the cooling coils. When specifying UV lights, be sure to consider cooling coil, UV light, and final filter arrangement. UV light can degrade a filter if there's not enough distance between the lamps and filter. This is most prevalent in a blow-through unit orientation where the fan section is not present to provide adequate spacing between the coils and final filter. Also listed here, which is a much less common application of UV light, is an in-duct installation. The intent for the UV light here is to disinfect the actual airstream. However, this is very rarely specified due to a variety of results on effectiveness. So we've discussed a lot about filtration and ventilation to properly remove contaminants from the airstream. However, equally as important is temperature and humidity control. Obviously, the primary source of high humidity in a building is the ventilation air. This is especially true in an environment where ventilation rates may be high, required more ventilation air. In these spaces, it's common to design a dedicated outside air unit that will precondition or pre-treat the outside air before it's delivered to various air handling equipment. These units help provide a more stable airflow to be mixed with return air at the zone level air handler. And an added benefit of that is that these dedicated units will also require a pre-filter of their own, which is just an added layer of filtration for the overall building. Benny touched on energy efficiency earlier, and one common practice to help offset the energy required to treat the ventilation air is to provide energy recovery at this level. And sometimes, often, this is a code requirement through the energy codes. This can be accomplished by using an energy recovery enthalpy wheel or air-to-air heat exchanger. These devices most often utilize exhaust air that's already conditioned to help alleviate the load from the outside air handler's cooling and heating coils, which ultimately alleviates central plant load. An example of this type of system is to the image on the right, which indicates an enthalpy wheel treating outside air using exhaust air, which is already conditioned to 75 degrees. At the zone level, it's also important to maximize zone level control and isolate spaces with varying occupant loads or uses. Review your zoning at an equipment level and be sure to combine similar spaces on a common distribution system to prevent load swings. Try to utilize terminal units where applicable to allow for effective local zone temperature control, and discuss with the building owner the intent for each space so that you can fully understand the load profile for each zone. It's also important to utilize the building automation system to help with zone control. With some proper programming, the system can help identify the trouble areas that we discussed earlier. The system can ensure and record temperature and humidity levels for critical spaces. It can monitor and record air changes, pressure relationships, and for some critical spaces, respond and correct some of these deficiencies. So jumping into an indoor air quality case study or example, there's been a lot of focus on indoor air quality as it pertains to COVID-19 over the past year and a half. As most of you already know, this is a virus that's spread via respiratory drops that are in the air that we breathe. And due to this, there's a major concern with occupants in an indoor environment with air that's being recirculated. Additionally, it's become a focus in healthcare environments where these patients are being treated amongst other patients who are already immunocompromised. In hospital, healthcare providers are seeing a pressing need to treat the large population of patients that need treatment for COVID while simultaneously protecting unaffected patients and staff, and doing so in spaces that weren't originally intended to be airborne infection isolation space. The massive influx of patients created an immediate need to alter or renovate existing HVAC systems to create new isolation space, better treat patients, and protect the healthcare providers. With the onset of COVID-19, most people expected new design criteria, increased ventilation, increased levels of filtration, and we did see some of these things happening and issued as a requirement in response to COVID-19. However, the most pressing need was to create additional spaces for hospitals to be able to treat these isolation patients. One common method that we saw was taking a typical patient room and modifying the HVAC systems to be able to accommodate an isolation type patient. Ventilation air. The makeup air that were required in these spaces would often be more load than the existing air handling equipment could accommodate. Some other challenges that we saw were simply finding space in the ceiling plenum to be able to route the additional ductwork for these new systems. So the image on the right is of a project in which we designed new systems to create an isolation space out of an existing patient room. This space was originally served from a dedicated ceiling hung fan coil unit with ducted outside air. Obviously, this is not a system that was originally intended or feasible to make up the air required for the new isolation exhaust systems or to properly treat the high volume of makeup outside air. So in this case, a new outside air handling unit was provided to pre-treat outside air and serve the spaces with makeup air. Additionally, fan filter units were installed in a vertical chase to provide HEPA filtration and help achieve the room's newly required air changes per hour. As you can see, the patient rooms after this renovation are negative to the adjacent staff corridor to ensure all air from the space is exhausted to the exterior of the building. Now, Benny, I think we'll discuss further requirements in a commercial type setting.
Yeah, Matt, as we go into what commercial buildings have done or are currently starting to do, the ASHRAE Epidemic Task Force responded very quickly with, as you kind of alluded to, a lot of best practices, things that we should be doing in buildings if we're not already. But looking at the commercial building guidance, for example, and there are others, there's guidance for schools and all kinds of different types of buildings. So check out that resource. But the things here are pretty much commonplace best practices, pre and post flush periods, follow ASHRAE standard 62 ventilation rates, maintain space humidity between 40% and 60%. This isn't always doable in buildings. In an office building, they rarely have humidification control. So you can dehumidify and maintain that 40 to 60%, but you can often in the winter, if it gets very dry out, there's really nothing you have the ability to do. As I mentioned in the retail example, don't cycle your systems while people are occupying the space, keep the ventilation flowing. As we just talked about, the high MERV efficiency rated filters are a good best practice. The cleaning happens often at night in buildings, and a lot of VOCs and other chemical compounds can be left in the space. And so consider operating during the cleaning hours to keep that information or that particulates out of the air, get it out before people occupy the space as well. Plus, it protects your cleaning staff. And one of the recommendations was to discontinue the use of that energy recovery wheel because of concerns over cross contamination. I think that's a case-by-case deal. A lot of buildings are designed for that energy and load reduction. And then recommission systems. As we're looking at occupied buildings, existing buildings, they may not have been designed at the time ASHRAE 62 had ventilation standards. They may not be operating as they are intended to. So commissioning and recommissioning is a very critical step. But the question has come up many times, is there a way to quantify this? Do I know if these great best practices that are being recommended for my building are actually working? You put them in place and people say, well, how do you quantify this? Or where should we be looking closer at things? So there is an equation called the Wells-Riley equation that was published years ago to help quantify the risk of infectious respiratory disease spread in buildings and spaces. This equation is very simple, very useful. And what it does is it helps you identify if you need to change something. If the ventilation of effectiveness of your VAV system is not keeping the risk number acceptable, you may want to look at portable HEPA units and for filtration in the localized space. And it depends, again, on what the space is used for. If it's a classroom, conference room, office space, healthcare environment, the requirements are going to be different, but you can quantify the risk. And air quality monitoring and testing is something that has really come into play. A lot of buildings would do a test per year and not really know what the data means. Have an industrial hygienist come in and take some samples and see what's floating around in that one day. But now the cost of sensors and the availability of decent sensors that can constantly monitor and trend and be readily available on a portable device to monitor are accessible and affordable. And so we're seeing people starting to put these sensors in buildings, but having to understand what the information means isn't always the simplest thing. I give an example here of an office building where we had a sensor located in a lobby and we're tracking total volatile organic compounds or VOCs. And we saw these spikes and they were near warning levels and there was concern that something was happening in the building. And at quick observation, we found that the spike was momentary and it dissipated fairly quickly. The ventilation was effective, but the spike wasn't concerning because it was happening due to reasons that we figured out. There was a cleaning crew coming through, or during the weekday, we saw a lot of hand sanitizer use when people were walking into the space and using the hand sanitizer, and it put off some VOCs into the space, quickly dissipated. A lot of different risk and health risk exposures are time dependent. So how long are you exposed to that? And Matt alluded to some of the EPA standards, and OSHA also has some guidelines that can talk about different chemicals and compounds that we might find in our air. Real brief case study on the cost of this. We did a case study in a building in Chicago, and we weren't able to actually do this because the building's not occupied. So we didn't use live data, but we put it in an energy model and simulated the cost of a couple different things. One of the recommendations was to do the purge ventilation, so the 3 air changes pre and post occupancy. Doing that every day of a working week, we found that it increased the annual energy of the building by 21%. This being a building in Chicago, it could vary different on your climate, but 3 air changes pre and post occupancy is a lot of energy. So you do have to look at these measures and understand, are they effective? Are they doing what I want? And am I willing to increase the energy costs of my building? The second one we looked at was the demand control ventilation, or reducing the ventilation when there's less people in the space. We looked at minimum ventilation, which is code, and then we looked at 3 different levels of ppm, or parts per million of CO2 in the space. And at 1,000 parts per million, which ASHRAE would deem, it's calculated, but would deem acceptable, we saw an energy reduction using the demand control ventilation. We looked at LEED has a requirement around 800 parts per million, and we saw that it increased slightly, but it's still below that code level. So it's a very effective energy measure. And then we looked at what a more recent wellness standard, the well building standard, has a threshold around 600 parts per million. And you can see that takes us just to above the code ventilation levels. So all of these have a minor impact compared to the purge ventilation. So it really comes down to how you want to operate your building and maintain it.
Awesome. Yeah. Thank you, Benny. And thank you, Matt. That is a ton of information to digest. And before we get started on the Q&A, I wanted to let you know what the audience responded for that second survey that was about building products or systems. The first and most used was air handlers. Next was rooftop units. And third was VRFs, or variable refrigerant flow systems. All right, so let's take some questions. Please type your question into the Ask a Question box and type the presenter's name before the question so that I know who should answer it. And we'll get to as many questions as time allows today. Questions that we do not get to will be responded to at www.cscmag.com. And to download the presentation slides for today with all those references and resources, please click on the event resources on the left side of your screen. And don't forget, you can earn 1 AIA CES approved learning unit for this event. You do need to pass a 10-question exam. And to take that learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab at the top of your screen. That will open in a new browser window, so please open it now if you do plan to take that exam. All right, gentlemen, let's take some questions. Let's see here. Benny, I'm going to ask you the first one. All right, let's see. What are the current recommendations for pre and post conditioning?
Sure. It's going to depend on the building, but when you go back to the ASHRAE Epidemic Task Force, the slide I just showed a couple seconds ago in the example, it started off as time dependent. It was hours of running the pre and post purge, but it got revised to being 3 air changes. So, air changes is dependent on the volume within your space. So it's going to be dependent and calculated on that building what your pre and post should be. But again, look at it from, is it a measure that makes sense for your building?
All right. Got it. Moving on, let's see here. I think, Matt, I will send this next one over to you. How does air quality impact energy efficiency?
Sure. So we touched on that a little bit in the presentation. There's really two major impacts that we see. Obviously, first is conditioning the amount of ventilation air that's required for a space. A good example is where I'm at here in Texas. We're climate zone 2A, so we don't often get to take advantage of the economizer sequence as often as Benny might in Chicago. So that's a major load impact and energy impact to the facility when you have a large heating or cooling load for the space. Second impact is for fan power. We really see this when we start adding filters and ultimately pressure drop within an air handling unit. Obviously, the higher the MERV rating and the more filters that you have in line, the more fan power that's required to push air through that system. So there is definitely an energy impact. We discussed on some ways that we can help alleviate that, one, by taking advantage of some of the general exhaust airstream and using energy recovery, fan power. We can try to make sure that we're obviously meeting the needs of the energy code and ensuring that our fan power doesn't exceed the allowable limits for a certain amount of airflow.
Okay, thank you. Let's see here, Benny, we have some more questions. The next one is for you. Can you, or how do you determine if a sensor is reliable, or, how do you determine calibration for sensors?
Yeah, that's a very difficult question. It depends on the sensor and what you're trying to do. A lot of times things aren't sensing the actual element. They're looking at a measurement of a gas that relates to it, and there's an offset or a calculation. So the best thing that you can do is to make sure you have a good maintenance program or preventative agreement where you're regularly calibrating your equipment. When you're setting it up in the field for the first time, you want to make sure you have calibration and test gas. You don't want to buy a sensor from off the shelf, put it in, and just assume that it's correct. I'd say in general, we do a lot of sensor work and commissioning of sensors, and we find you can't always trust what they say. So as far as looking at it, you want to find people that have reputable certifications and that talk about the calibration process for their equipment and are transparent about it.
Sure. Okay. Let's see here, Matt. The next one is for you. When is it beneficial to design for increased ventilation above code requirements?
Sure. So I see three different times or three different scenarios where it may be beneficial. First is just a simple conversation with the owner. There may be instances where the owner accepts that they may want to provide more ventilation for the space, and there's just a pre-designed type discussion that we plan for that type of additional airflow. Second conditions may be sort of helping alleviate the difference between what's put on paper and the conditions we see in the field. What I mean by that is discrepancies in what the fans are capable of doing, duct leakage, accounting for that. It's often ideal to if a space requires 12 air changes per hour, we may provide 15 air changes per hour, anticipating that there will be some duct leakage, and we want to be able to provide what the actual code minimum is. And then the third instance that I see for providing additional ventilation air is if you're anticipating a potential code increase. We see this often in healthcare where the ventilation tables, we know that maybe the state is discussing a potential increase, and the owner says, well, we're designing this, the new code may be adopted in a year from now. Let's go ahead and provide what we think the additional air changes may be for that time so that we're not in an instance where we're grandfathered in.
Okay, gotcha. Let's see here, Benny. Next question is for you. Is ventilation effectiveness dealing with the amount of fresh outdoor air being provided to a person at the nose mouth area of the room? So where are we measuring this ventilation?
You're probably tired of me saying it depends on the design of the space, but it's dependent on what you're looking at. In an office, you're going to have seated occupancy. So, ASHRAE has a standard 55 that looks at thermal comfort, and it evaluates down to what shirt you're wearing that day to what kind of insulative values does it have to determine comfort. So we're going to look at the occupant zone, depending on what they're using. A person in a warehouse or a manufacturing environment is obviously going to be able to tolerate a higher temperature than a person sitting and working at a keyboard all day. So when we look at ventilation effectiveness, it's what is the effectiveness of getting that fresh air, the minimum required by the standard, to the person at their breathing level. So if I'm in a standing I guess I wonder if they'll have to maybe look at changing the office environment for standing workstations, but the standing versus sitting is definitely a different level. So you want to look at that, and that's why in the HVAC systems and how they distribute the airflow and what temperature that airflow is distributed at can make a big difference. Excellent, thank you.
All right, we have time for one last question, Matt. This one's for you. When do I have to use FGI, or Facility Guidelines Institute?
Sure. So that one is actually a pretty simple response. For that, if you're designing a healthcare facility, look into the state that you're designing that facility in and what their licensing regulations are. Some states will purely adopt FGI as a method of plan review and construction inspections. Some states, as I mentioned, Texas will adopt a certain code and issue a plan amendment or an amendment to that code as their adopted code. So for whatever state you're designing the facility in, look at the state licensing regulations and better understand exactly what the hospital is required to be designed to be able to obtain a license.
All right, good to know. Well, thank you. And I'd like to wrap up by thanking these extraordinary subject matter experts, Benjamin Skelton and Matt Short, for sharing their extensive knowledge of HVAC systems and indoor air quality. So I'd like to extend a special thank you to our sponsor, Aegis, for supporting this education session. Before we go, we need your feedback. So please take a few moments to complete a short survey that will pop up on your screen as soon as this webcast ends. We do take this information to improve future education sessions. Finally, on behalf of Consulting, Specifying Engineer, and CFE Media and Technology, thank you for joining us, and we'll see you again at the next education session. Thanks, and goodbye.